everyone, and welcome to Live from the Lab. This is a show where we talk about different technologies that Bruker's developed to help scientists discover the world around us. Today's topic is a really exciting one. We have a brand new X-ray diffraction benchtop platform, the D6 phaser. Now, the D6 phaser is all about power, versatility, and accessibility. Now, today's topic, we are going to talk about that accessibility point. What is accessibility? Well, this instrument is designed to be used by everyone, everywhere, and for everything. Now, as we dig deeper into those topics, we're going to learn about things like ease of use, affordability, and also just the general enclosure itself, how the instrument inspires confidence in its users. So to learn a little bit more, we're going to head on over to a video. Hello and welcome back to the studio. So we have a real machine. This is a real one right here. That was real in the commercial too, though.
It was.
And I'm also joined by Nate.
Hi, everyone.
So Nate is back. Thank you for joining us on Live from the Lab again.
My pleasure.
So the D6 phaser. Now Nate actually has a connection to the phaser family.
I do. It's
right?
USB-C. No, so the D6 phaser, which I think about as being sort of the spiritual successor to the D2 phaser,
Yes.
which many of you are familiar with.
Yep.
The D2 phaser was actually my instrument when I started out with Bruker. So, over a decade ago, we had the little diffractometer with the smaller scientists.
But even though it was small, we found that it was very useful by a lot of people, right?
Right. And so one of our original commercials a million years ago had me saying something to the effect of, wow, I really wish I had this in grad school. I could have collected my data faster.
Yeah, I remember that
right?
one.
Oh my God,
yep,
right.
Yep. You will always be known as that,
Will always
Nate.
be known as that. But, it represented something that was really cool and sort of groundbreaking at the time.
Yes.
Right? A small, compact, portable diffractometer that did powder diffraction exceptionally well with all of the infrastructure things that Bruker's known for, like our link side detectors and software like Topaz. And so it was really a revolutionary thing for us because it collected exceptional powder diffraction data, and you could put it literally anywhere. It was really groundbreaking at the time to have something that had internal cooling, and it had sort of the internal PC, and so it was something that you could put in a nice tidy little spot. And I remember in undergrad we had one diffractometer on campus. Thankfully it was in chemistry, so it was in my department. But then I went to grad school, and our diffractometer was like the other side of campus. So I remember during the winter taking my little box of samples and like shuffling slowly through the snow and the ice to try to not fall over and drop my samples to go over to the characterization facility. And I think that in the context of things like accessibility, that's one of the things that I think of first and foremost with the D6 phaser is the fact that you can put it anywhere.
That's right.
So it really opens up the idea of diffraction or this technique to a lot of industries and departments in fields where maybe diffraction was sort of inaccessible. It was either too expensive, it would take up too much space. We don't have the water, we don't have the power for it. And I think that that's something that our developers did a really great job of, was designing something that feels accessible.
Yes. So in terms of that accessibility, when we think about, and you were touching on this, it's for everywhere.
Yeah.
So you can really put this anywhere you want. Now it's not as light as the D2 phaser was,
a little bit heavier.
So this one, we would say it's transportable. Right. So the D2 is more portable. I mean, you could, I guess you can move it all the time. This one, you're going to want to put it on a nice table. This one has wheels. You can actually roll it around. But it does weigh, I think it's 350 pounds.
Yeah. And that was one of the things that we found out. So we did, I think we did a really great job of talking to our D2 customers whenever the D6 was being designed and getting the feedback of, what are the things that you really liked? Let's incorporate those. Let's keep the heart of the instrument the same. And one of the questions that went out was, for your D2 phasers, like, how often do you relocate it? And we found that not too many people were relocating it often. They wanted the idea of transporting it or moving it, right? But it wasn't a weekly or a daily basis or anything like that.
Right, and most of them, like for an academic, some people were pushing it from lab to lab, something like that.
Or they bring it out for like a teaching lab.
Yeah, you could do that on a cart with this machine, no problem. Actually, you could get a cart like this just from a hardware store or something, and that takes the weight. But we've also incorporated some really nice handles, right?
So we have these nice, heavier than you would think, right? So really, really well engineered. And so these screw directly on the side, and then you can lift this up. I think it's probably a 4-person lift.
It definitely is. I mean, 4 handles.
Four handles, 4 people.
The way I like to think about it is that your car, right, has 5 lug nuts. You don't want to be using 2 of them. So this has 4 handles. Get 4 people. Lift it.
But I mean, the cool thing is, so we're here in our recording studio in Madison, Wisconsin, and this was wheeled over from my lab.
That's right. Yep. We just pushed it right in, plugged it in.
20 minutes, you're up and running.
That's right. So, and now this is a 600 watt version, but we also have a 1200 watt, and either of them, though, don't require the water, right?
Right.
So they both have internal water.
So we've kept, again, so in the context of keeping, the spirit of the D2, right? Keeping that heart. One of the hallmarks of the D2 was internal cooling.
Now, if you do happen to have water chilled in the building, water chill, whatever, if you're very sensitive to heat in a room,
we've got the option to do external cooling as well.
You can get that option too, the external cooling, but just to reinforce that even the 1.2 kilowatt, you can do the internal water chiller, and it doesn't heat up your room like crazy or anything. So that's kind of the everywhere, and you can still use it everywhere. I mean, still you could put this thing in the back of a truck. You could put it into a mobile lab.
It's been in the back of your SUV.
That's right. Yeah, I actually, to film that video we just saw, I actually put it in my SUV and drove it to that studio. So now let's talk about the whole everyone, because everyone, that was a very important tenet too with the previous phaser. It was about that anyone can really pick it up. You don't even need experience with diffraction, right?
Exactly. And so one of the things that I really appreciate is, so this small little touchscreen right here, right? You can actually push your experiments to it. So for those of you who are familiar with our software packages, we have these job templates, right? And on the computer, so we still have a computer here, that way, right? And you can, you still operate it from the computer. You can design your little templates that say, I'm say you're in a laboratory where everyone has their own project, but they know that they're going to be collecting the same scan effectively every time, right? You go up, click the button, type in your sample ID name, and then put your sample.
That's right.
right,
That's right.
And then start it. And so those buttons can now be pushed over to the touch screen. Right. So if you have something that you're going to be repeating over and over again, you go up, push the thing, and then it will create a unique job identifier, which then links back to our database, so you can reference it and say, oh, it was job 364, and that's the one that I want to go back and look at. So the accessibility part of it, I think, is key to making sure that as we expand diffraction to other industries and sort of non-experts, right? People aren't terrified.
That's right. In fact, I would take it the other way. I think this machine, more than any, I'm not even going to say any XRD, but any analytical solution I've seen, has done more to inspire confidence in the users. It's gone further in that realm, and I think that's key when you start changing things. We'll talk about everything, so we have a whole host of different accessories here we'll go over with everything, but like you said, the screen here, actually, like right now, it's got a little green square. And why does it have a green square? Because we ran a measurement. We pushed the button, and it said verify the instrument. So it ran the corundum, checked 4 peaks across the entire measurement range, made sure they were in spec.
So you have confidence that you're aligned.
Bam, you know it's aligned. Even if you changed something, you know you did it right. Right? And also, if you change your configuration, like Nate said, if you have a certain method here, I'm going to do stress, I'm going to do texture, it also validates the setup of the machine.
Particularly for these techniques like stress and texture, where you are very, very sensitive to peak positions, right? You need to know that any sort of variance is coming from your sample and not from your instrument because you did a configuration swap. And that was one of the challenges as I moved from the D2 onto the D8 and the D8 Advanced and the D8 Discover platforms was, with all of these stage exchanges, right? How do you build confidence that that the center of your instrument is the center of your instrument, right? And I think that the designers have done a really, really great job with the D6 of making sure that this feels sort of intuitive, and you can build that sort of confidence for people who may be learning a new technique for the first time.
So whether you have no experience, absolutely none, or you are an expert, this machine really, really does feel right. And what I mean by that is if you're an expert, it also doesn't feel like you're being babied. It doesn't feel like Clippy bothering you all the time.
I forget about Clippy.
Right? I mean, even as the group here, as I've talked to everybody who's used it, they appreciate that I can press that button and then it's going to tell me the machine is all set up and that it's set up right. So with that, let's talk a little bit about the everything.
You want to open it up?
So let's open it up, and then also while we're talking about everything, one of the ideas with accessibility and everything, we're going to see a lot of different stages here, and what we did was we made it so the machine is really easy to add on to, and the reason for that is because what we've noticed, after selling machines for a very long time and enabling people with our solutions, is that there's this cycle. Every 10 years, I'm going to buy something. And then I don't buy anything for 10 years. And man, we go to those sites.
It's like a hot water heater. You buy it once, you don't want to think about it.
And it's amazing because sometimes then you go there and you go to a site to do a training or work with the people, and they have all these parts that they've never touched in years.
But it was insurance.
But they were trying to say, well, okay. But at the same time, that's an opportunity cost because now they spent money on that where they could have spent it somewhere else, right? So the idea is here you have many different parts that you can buy, and we're even probably gonna put these on the web store, a lot of the parts. You can buy them in the future, and then you can add it, and they're all low cost. So it's really, really easy to expand it moving forward. You don't have to think every 10 years I have to enable myself for 10 years. Rather, get the platform, and then during that period that you have the platform, you can always add capability.
I thought about it a lot like building a gaming PC, right? You need the core. You need your processor. You need your graphics card. And so, for the D6, you have to decide what kind of generator am I going to use. What's my power, right? You need to decide how am I going to do my beam shaping. I want to have a fixed slit or a variable divergence slit, and then the detector, of course, the hallmark of Bruker products is our Lynx-I family of detectors. But once you have that, if you want to upgrade your RAM, if you want to add in water cooling on your PC or something like that, you can do these things along the way. And I think that that's kind of how I think about the D6 is that it's designed to be upgraded in the future if the need presents itself.
That's right, and we don't even know. the way the materials communities are changing, that just research in general is changing, we can't tell you what the hot thing is going to be 5 years from now. But what we will do is this, is that 5 years from now, if a need arises, we'll design a new accessory so that you can make those measurements on the platform. So speaking of that, let's talk a little bit about some of the accessories.
Sure.
So we'll go more into like I guess into the slit and the generator and the lynx eye and the power episode. But the first thing you can change though is the X-ray tube itself, right?
The tube itself, yeah.
So we support a whole wide range of wavelengths, right?
So what we have right now is copper.
Yep.
So copper diffraction, pretty common. It's one of those bread and butter type situations. But if you needed to switch to, say, cobalt, because you're in a geology field and you're expecting peak positions in a certain location. So if we look at the top over here, so you can see that the tube itself has these 2 screws, right? And so it's simple. 2 screws come out, the whole tube lifts out, and you see that we've got this sort of like nice clearance area, right? So it's designed to be swapped out if you have an application need for it. So we do have an on-demand special request option to also support molybdenum radiation. So if you're looking at harder radiation or higher energies for something like, say, like PDF, you have the option as well. And it's as simple as take the tube out, drop it in, and then if we switch to the other side of things, so here on our detector side, our detector itself also has the option for accepting different X-ray wavelengths, right? So whatever tube you put in, you have a matching detector profile. So it's basically a set, right? Which is really nice because you don't have to go through any sort of long process to get that up and running. Change your tube, push a button, and the detector will update to say, oh, I know exactly what types of X-rays I'm trying to pick up.
Yeah, and even the standard slit or the advanced optic, all of those are also wavelength agnostic. So
exactly.
You can just drop it in. One other thing I'd like to note with that tube change is you don't have to turn off the water. So when you turn the machine off to make that tube change, it'll depressurize that water system. You just take off the screws, you're good. If you get a little dribble of water, then just wipe it up. But you don't have to disconnect hoses, things like just drop in the new one. You're good to go. So very, very easy. Another dynamic bit, right? That you could change. Now we also can change the little bits, right? So slits and things like that. So we've got, our slits here, that type of thing. And then on the detector, you can also change some parts,
right? And so if we look at, say, the idea of taking a sample for everything, or like designing an experiment for almost anything that you could run into. So slits. So for traditional powder diffraction, right? It's very important to make sure that you're matching your application needs. So do I want more intensity? Do I want more resolution? So this one here, we have a variable divergence slit, so it's a motorized divergence slit. We also have there's a solder in here. And this little panel actually just slides right off. And then you can access the solder. So if you need to switch out a solder to do something bigger or smaller, depending on whether you're looking for, say, more intensity or maybe a slightly sharper peak, easy enough to grab. Same thing on the detector side. Okay,
and that's one of those little designer things too, right? So if we look back at this, on the previous machine, these holes were actually just holes, right?
Right.
And now they're keyholes.
Exactly. So I don't have to worry about losing my screws.
You just take it out, put it in. There you go. Now you can change those solars, and when you change, it's really surprising. You go from 2.5 solars to 4 degree. You lose a little resolution.
A little bit.
But the gain of intensity is amazing, right? What do you get?
It's about a factor of 2 on each side.
A factor of 2, just in solars.
And so I do a lot of support for the pharmaceutical industry. And one of the challenges that's presented itself to this industry is they want to make out very, very small amounts of impurity. And if you think about it, if you're taking a drug, right, you want to make sure that it's the thing that you hope it is. And so one of the easy ways to sort of boost your sensitivity is just to have more X-rays. And that's a really, really easy trick for that, is to use a larger solar slit.
So then on the secondary side, you could do the normal axial solar.
Same thing. So we've got another solar slit here. So simply push it out, remove it, and we might come back to this side as well.
And then we also have other things. So we've got, for example, this piece here. This is called the telescopic slit shaft. And this is for X-ray reflectometry.
Capillary diffraction.
That helps with the background.
Well, I mean, I thought that this was a really, so we'll talk about the stage in a little bit, but capillary diffraction was something that I didn't do a lot of in graduate school. We just didn't have enough material for it. But the idea of like sliding this out, you can put this slit very, very close to the capillary, and basically you have sort of like a flight path, which cleans up the beam, as you get lower and lower. So for people like pharmaceuticals who are doing sort of this low angle work, it's nice to have this and sort of just clean up your signal along the way. And this fits exactly in the same location as the exosolar.
And then if you're doing some sort of parallel beam type diffraction, so GID and such, then we have the equatorial solars too.
So this is exactly like an axial solar, but it's rotated 90 degrees.
Yep, and those are available in different sizes to emphasize resolution, things like that. Again, we'll talk about more versatility in the third episode. But those are all things that you can change. You can change them easy. You go there. Now, we kind of skipped over the middle part. Let's go back to that because we got a whole myriad here. So powder stages. Now, first thing you got here is like a fixed stage, right?
Fixed stage. So for people who maybe don't need a lot of complication in their lives, right? The fixed stage is designed to hold any of our standard sample holders. Okay, so I'll actually pop this one out. Okay, maybe did that a little bit too fast. But this is our corundum plate. So this is used for verifying each of the stages. So you'll use this part for the fixed stage, or rotation stage, maybe some of the universal things that we'll talk about in a little bit. But then this is a standard 51 millimeter sample holder. So that slides right in. If we go back over to the stage itself, what we can see is that this will then slide right in and lock into place. Okay. So we've got an air scatter optic here. So this is for cleaning up the beam at low angles. So for those of you who have gone below 20 degrees, you might have seen a little tail in your data. This is great for cleaning that up. And the cool thing about this fixed stage is we didn't say which way it's fixed.
Yeah, that's right. That's right.
So you can do this in a traditional we do this in a traditional reflection geometry, right? But you can also rotate the stage 90 degrees and do it in transmission. So flat plate transmission.
Oh, really? So you can turn this now. Maybe that's a great time for me to challenge you. Maybe if you could actually show us how you do that. How do you take a stage off like this? How do you put one on? Maybe just switch it from reflection to transmission.
For sure.
That'll give us an idea.
All right, so let's see where the cameras are. So we have our screwdriver.
So one thing that can be useful, it does come with wrenches, but we found one of these electric screwdrivers, and that makes this really easy. Any
opportunity to go to the hardware store and buy new things, right?
Absolutely.
Okay, so that one, two underneath it. I think for, okay, so we've got 4 out, right? So then this can simply rotate. Hold that.
Oh, sorry.
Sorry. So this simply rotates 90 degrees. Okay. Slides back in.
And when you put that in there, it's like stuck, right? Like if you take this and you try to like wiggle it.
Yeah, so there's there are little cutouts, and I'll show you on the next stage. Okay, 2. So I know that several of my colleagues are car people, and they always talk about the precision of German engineering, right? Yeah. But I get it. I get it with this thing. But so now we're actually set up. So if we had a transmission set up, we would slide our sample in this way, right? And so then the beam's going to be going through the sample.
Yeah, and of course you'd use a transmission holder. Right. In that case, you wouldn't use that flat plate.
You would have some sort of Mylar or Kapton or something like that to do it. But
so it's really easy to exchange these stages. It's really and like you said, when you put it in, it's surprising how well it fit. I shouldn't say it's surprising, but it just fits well.
Well, and so let me actually give you a little preview. So our next stage that we'll be looking at is going to be this rotation stage. So for those of you who have experience with the D2 phaser, this will look very familiar to you, except this one comes off.
That's right.
Right. And it's designed to come off. And if you look at the back side of it, there's this nice little cutout right there, right? So this is machined out very, very precisely.
Yes.
Meticulous, right? And so when this little slot is on there, you know that there's only one direction that it could go in. So obviously with the fixed stage, there's 2. One flat and then one at 90 degrees. And then this seat is very, very tight. Right. So you know that whenever it's on, this is one of the things that builds confidence is that you've got this. You know that it's really precisely mountable every time. And then whenever you take the corundum plate, slap it in here, you would have the same.
That's right. And to build again that confidence, you just press the button, and then the method lasts about 7 minutes, checks the 4 peaks of the corundum, and it's going to tell you, it's going to give you, actually in the software, a green smiley face, and it'll say, system is ready.
Yeah.
So if for some reason it didn't, let's say that you end up getting the red face, there's another button you press. And then what it does is it'll actually go through and calibrate the machine.
Yep.
So, or reference the machine, I should say. So that's a really, it's really, really easy to change these things.
Yeah.
So we got the rotation stage.
So single position rotation stage,
Okay.
right? So traditional powder diffraction.
Yep.
If for some reason you have, say, poor statistics, or maybe you've got like a silicon wafer because you
Yep.
don't. So I worked on nanomaterials in
Yep.
grad school, and we weren't making a lot of powder.
Yep. Yep.
And so on a silicon wafer mount, one of the things that our trick was to spin the sample. And
Yep.
so as we rotated the sample, we were able to access more crystalline directions,
Yep.
more orientations, and we were able to basically trick the instrument into thinking we had more material than we had.
Yeah, if you have those minor phases, then rotating really helps you, can help
really
you
help
out.
out with that.
Yeah,
Exactly.
get into the beam.
So one position, not
One.
rotating.
Yep.
One position with rotating.
Yep.
And then what I
And that's
really
both rotating, like always rotating, and also you can set.
index at 5.
So, yeah.
Index 5, right?
All right.
And then the other one that I'm really excited about getting to play with is this one.
Yeah.
So this is 12 positions.
Not 6.
12 positions
Not 8.
rotating. Right. Yeah.
12.
So these accept our smaller sample holders.
Yep.
And they will. Trying to figure out what to do with my cables, right? These would normally be hooked up to the instrument.
Yep.
So all of these go in. You can see there's nice little marks on it. And then there's a little elevator that will lift it up into position underneath here.
Yep.
Right.
And when you change these, by the way, the connectors in the machine, they're located
Close to it.
really close to it.
Right.
And the motors themselves, they have all the driving electronics right on the motor. So
Yeah.
you don't have to worry about if I add a stage, I have to add extra boards, stuff like that.
So this is
All
again
comes in.
one of the really cool things that I think our designers took to heart whenever they came up with this. Is it's what they call it, the CAN bus technology, right?
Yep.
And those are all designed so that on the larger instruments you've got to run a cable all the way through the labyrinth and get down to the boards. And these are all. I mean, like that's not really that long of a. I mean, that's USB.
Yep.
Right?
Yeah, that is.
Yeah.
Yep.
And so the idea that you don't want to have a lot of dangling cables, you want things to be close to where they need to be.
Yep.
It's one of those things like when you plug it in, it should feel like that belongs there.
That's right.
Right.
So then also for powder, we have a capillary stage, right?
We have the capillary stage. We don't have one yet.
Yeah, we don't have one here.
I
do
asked
have
for
it. It is
I've
real.
asked for a lot of parts,
Yeah.
but we just got this in the lab a few weeks ago.
Yep.
So we're
Yep.
slowly consolidating all of our parts, but it's kind of like Christmas. But
That's
then
right.
like a week later, your mom finds a present
Yep.
in the closet. Is like, oh, and by the way.
Yeah, and that's great for doing PDF measurements,
Yeah.
structure determination.
And for things like orientation. So if you
Yeah.
tumble your material in a capillary, you can kind of massage out some of the orientation effects.
small quantities of sample,
Anything air
precious
sensitive
samples.
that you want to
Yeah.
sort of protect from being exposed to air.
So if you head on over to the website or even YouTube, there's another video up there where you can actually see what the capillary stage looks like.
Other powder,
Another powder.
non-ambient.
That's right. Yeah,
Yeah.
sometimes we don't want to collect
Exactly.
at room temperature.
So
right?
again, we'll get one.
Yep.
I have a list of toys that I want
Yep.
to play with in my laboratory. But so the non-ambient, historically for us, has always been on sort of the larger floor standing instruments. And so with the redesign of the phaser enclosure, we have quite a bit more space in through here.
Yep.
So we can now accept the BTS 150 and the BTS 500 stages.
Yep.
So whether you need to go to 150 or 500,
Yeah.
same idea. So there's a central mount. It will get placed inside of that. There is a controller. I think it's one of them is USB. And then all of that is just seamlessly integrated into our software. You don't need to
Yep.
have a external program or anything like that. You simply go into our software and say non-ambient, tell me my temperature, tell me how many scans to take, and then you can design a host of...
Yeah. You go into the wizard right there.
Exactly.
It will guide you through setting it all up. So, and you don't, even though we have that non-ambient chamber, which say it's at 500C in here, you don't have to worry about it heating up inside. I mean, they're designed to keep things cool, but the machine itself also has a lot of airflow. In fact, one of the cool things, and since we're talking about accessibility, if you ever have to change your air filter, you just pull a little thing, and welcome to my little friend here. This is the air filter. So you can see, I mean, we are really flowing a good amount of air through there to keep the system nice, cool, and stable. So you just slide it back in when you need to change it, and that's it. So
Actually easier than my air filter at all.
that's right. That's right. Okay, and then also sometimes you might want to have some sort of a motorized air scatter shield, right?
So we had so there's the fixed one here that goes on to either the fixed stage or things like that. We also have a motorized air scatter. So for those of you who are doing low angle work, say like clays or pharmaceuticals or zeolites or something like that, historically the low angle data has sort of had this kind of tail. Right? Which can really, really obscure some of your low angle features or maybe give you a little bit less confidence in terms of the intensities that you're measuring. And so on our floor standing instruments, so the D8 Endeavor, the D8 Advances, we had this, we call it the MASS, the motorized air scatter screen. And it was so well received that we designed a version of it for the D6 phaser. Right. So it's kind of cool to see things that really cut their teeth on our flagship diffractometers, like the D8 Advance. So things like the XCT detector, things like the MASS, things like motorized slits. Eventually, they've made their way down to our smaller footprint instrument. So you're getting all of the accessibility without really sacrificing anything in terms of data quality or measurements or
and this is part of the whole dynamic beam optimization, which we did a previous episode live from the lab from. So what that is you just type in the size of your sample. 15 millimeters or whatever the sample size is. It will adjust the size of the beam. It will adjust the position of the mass, and you can even have it open and close the detector opening. So that you get the best quality data automatically. Right. And adding this, by the way, say you don't get it right away. It's really simple because if we look inside of the machine here. Right up here, there's actually a little piece where it mounts. And then the connector is right here. So, if you want to add it in the future, you just buy it, you get it, stick it in, one screw, done.
So I've been really excited about playing around with this one.
So powder, you can see very extensive. Now, to support higher, or I'm not going to say higher end.
Materials.
A broader scope of methods, we have what's called the universal stage. So, and I look like I'm struggling because this is heavy. And what this has is it has the ability to move the sample height up and down. So you have,
Z.
You have several millimeters of motion. I think it's plus or minus 3 or plus or minus 2 millimeters. And then it also has the ability to tilt the sample. And what that means is that in our goniometer, now the phaser has this really innovative goniometer where the arms actually move up and the sample moves down. So it keeps that coupled condition very precise on a benchtop. This gives you the ability to offset that condition.
You're decoupling.
Decoupling.
Yeah,
so we're decoupling the coupled.
Stage motion.
And now what I can do is I can do measurements like texture, I can do residual stress.
Raising incidence diffraction.
I can reflectometry. We've even been playing with RSMs. So
stay tuned.
Stay tuned to that. This really opens up a whole world of possibilities because now we have tilt. So,
and so if you want to hold that, what I can do is I can show you how we build on it. Hold the heavy part for me. Okay. So this, as John mentioned, this adds 2 different motions.
Z.
And then an offset. So like an omega offset. Right. So on top of this, what we can do is we'll start with something simple. So this would be turn it that way.
There you go.
This would be a standard spring stage, right? So let's see if I can do this without knocking it out of your hands.
So if you have any of our other D8s with these types of stages,
so of course I would screw this in on the instrument itself.
But 4 screws. Exactly. You always use 4, like the 5 lug nuts.
And so this would accept. So we call this our universal stage. It should be able to accept everything. So much like the fixed position for powder diffraction, we have the same thing here. So the spring stage will accommodate that. Maybe larger parts. So if you had like a cutout or something like that, that would work. So that's one of them. The other one would be, say you have a very small sample. So this is just run that cable 8 ways. Okay. There we go. Is a vacuum finger.
Okay.
A little vacuum finger. So this again mounts on it this way. Oh, no, got it the other way.
There you go.
Front way. And so this has a little, so this will connect to a little, like a vacuum pump. Very small one. And then there's a little hole on the top of this. So like if you have, so I think your graduate work was with
thin films.
Thin films, very small thin films, because they're expensive to make.
That's right. So we make those little 5x5s, 10x10s, but you could even put a little bit larger wafer on here.
And the idea of this suction is that it holds it on the tip of it. right?
Yep.
So that as you're changing your angles and you're accessing all of these sort of off-axis reflections or something like that, you have the ability to not drop your sample.
Yep, and you don't have to worry about the tape bending or bowing or
getting the tape back off of the backside
that's right,
of your substrate.
when you're removing it, so that could be a problem too. So, and Nate said, like he said, there's the vacuum, and that actually there's a nice labyrinth, big labyrinth in the back where you can run those things through.
That one's kind of cool. What else do we have? Oh, and our last one.
There we go.
So this adds a third variable
Another
on top of it.
axis,
So we've got Z.
Yep.
We have
Omega. Yep.
Now we have.
And we have theta, two theta. Okay, we have two theta then.
Right.
Yep.
And now we have phi.
All right.
Indexed phi.
Here we go.
Right. So phi
you can
goes
put
on
that
top.
guy on there.
I'm just gonna not. Right. So a little bit heavy, but what this allows us to do is then change the angle. So if you're doing in particular stress or texture, right, you need the Z to be able to access very specific heights of samples, right, to really, really fine tune your sample alignment. You need to be able to tilt your sample in order to access all these different directions that you're pointing your sample, and you also need to be able to rotate your sample. So particularly for things like pole figures, right, I need to see 360 degrees around my sample. And so with an index phi, you can do that. And so this will accept a standard sample holder. So if you have something about this size, right? So I'll just tilt that forward. Let me see. Yeah. So this will accept a standard sample holder, right? Easy enough. It also has the ability with these little cutouts. So the lab next to mine has a lot of our microscopy solutions, and they often will get epoxy mounts. So met mounts or metallurgical mounts. And so these are designed to accept different heights of epoxy mounts, so you can just slap them in.
Yeah. When I was working in a foundry, we used to always mount those to polish them for metallography and such, and those will fit right perfect in there.
Exactly. So you take the same sample, move it from the electron microscope, then you take it over to the diffractometer, maybe you take it over to a tornado for elemental mapping. You've got all sorts of different things that it's designed to accept.
Yeah, so you can, and as you can see, you can build these parts on. You can always add them. And so the bit of accessibility here, again, it's both that you can always be ready for that next measurement, but also when you first buy it, maybe you don't have every single part. Maybe you don't need them all. Then you can, have a lower price on the core machine, and then add these things later as time goes on.
And it sounds really dumb, but one of my favorite things is, so you've got all these screws in there.
Yep.
They're capped.
Yeah, they are. And those are the little things that you'll find about this
because
enclosure.
I'm always running around trying to find, if we could find a way to get the one wrench that I need in my lab to always stay in my laboratory, but finding the right screws for a stage, right? They're on the stage.
That's right.
They're just there. Yeah.
So we've got all kinds of things to talk about, but what we're going to do now is we're going to get to some questions. So the first question is from Basharat, and that question is, can we detect the small angle spectrum on the machine? How much small angle? So I think low angles.
Low angle. Okay, so I have done, being a diffraction, so diffraction specialist and with powder, I've gone down as low as, say, 1.5 degrees. 2 theta, right? So we've got a really great powder, not a great powder, it's kind of greasy, but it's called silver bayonet. And so it has very regularly spaced peaks. So it's often used to measure how low can you actually go with a diffractometer, and it's got a peak around 1.5 degrees.
So, and on this machine, with the with the variable slits, with the mass, with all that stuff, what we've actually found, you can very reliably measure down to about 1/2. So you can even push that farther into that small angle region. From Chow, the question is the signal from the D6 phaser comparable with the D8, Endeavor or Advance? Could we have D6 as a backup or instrument for method development, then apply to the D8?
Yes, okay, so signal. So the question is always how do you put a metric for that? Right. And so one of the ways that people will look at this is in terms of just raw power. Raw power is a little bit of a bait because the true thing that you should be measuring is either peak to background or signal noise ratios. And so with the D6 phaser, we've talked about the different power options, which we will talk about in one of our upcoming episodes. But 600 watts or 1200 watts are probably going to be the two most common ones. And even at 600 watts, which is a bit below what our D8 Advanced often operates at, which is usually about 1.6 kilowatts, because everything is very close. Right. So we have a much smaller instrument radius from tube to sample, sample to detector. We end up actually exceeding the observed intensity
That's
in raw
right.
count numbers, right? So I always tell my customers and the scientists that I'm working with, intensity is just a number, right? What really matters is relative intensity between the peaks and then from the peak to your background.
Yep.
Exactly. Because you can always get more counts by counting longer, but then you also increase your background as well, because you're counting the same for everything.
Yep. And with this question, yeah, my answer would be that let's just say you might have to turn the D6 down. You might have to turn the power down.
It's a lot of intensity.
If you want to.
I've been pretty happy with it.
Match the signal.
But I think that the second part of the question is can you use it as a backup or for method development?
Yeah.
I think so. I do think that in the context of any sort of regulated environment or anything where you do have a very specific compliance, that method itself, if it is, this is something that has to be defined at the the customer level at that site, is if it needs to be if it's specified in a D8 Advanced and you have to do everything exactly the same, then you probably want to keep it on the same instrument, right? Yep. I think that you can certainly look at things like equivalency, but because there is a slight difference in radius, right? There is a difference in terms of power. There is a difference in terms of sampling volume, depending on whether you're using a fixed slit or a fixed sample illumination, right? Like those kind of things, they're subtle. But say a 0.6 millimeter slit on a D8 Advanced represents something fundamentally different than a 0.6 millimeter slit on a phaser. Right? So the phaser, because it's a smaller instrument radius, you're not going to have quite as much time for the beam to diverge. So you're going to be hitting different amounts of material, which will then give you different amounts of sensitivity and different amounts of signal. And so I certainly think it's something that could be considered. I think that from what I've seen with early testing of this instrument, there's nothing powder-wise that I can do on the Advanced that I can't do on the D6. The question is exactly how do you define equivalency?
And that's a good point. Even though, yes, absolutely, you could get the signal, you have the mass, so you could put the mass now on it, you got a variable slit on it, XET, you got all the right parts.
Same size sample holders, right?
That's right. But you got to check it. You got to have some document that says this is this, right? This is equal.
And we've run into this before with something as simple as changing the radius on a D8 Advanced. Right. Well, it's a D8 Advanced, but it's at 250 versus 280, and so you just need to be very thorough in method transfers. But once you have that, number one, it can be done, and then once you have that, then you've got a very clean. It is nice to think about as a backup because, well, so some of our, I guess, more engineered problems. So the high-end D8 Discovers, where they're doing a lot of RSMs or something like that, they're certainly capable of powder diffraction. But with the D2, we found that a lot of people, if they wanted powder diffraction, they had it off to the side. And if you need, phase ID or quantification, you just take that sample over to the D2. Right. Same concept could happen with the D6 phaser. Is if you have sort of a very engineered, specific, tailored diffraction solution, but then you wanted to have sort of walk-up access to sort of your more routine powder type things, like you could certainly think about it that way as well. And when we speak of backup too, sometimes we think about, okay, we're going to use the entry-level machine, but the other thing to think about this machine is it's not entry-level. Right.
When you talk about all these things, these are the most advanced diffraction methods that you now have access to, and because of that smaller measurement circle, the signal we're seeing is just absolutely astounding. So there are times when this is the right machine versus the floor standing unit.
Well, and again, talking about as we build sort of these like different stage modules up. I'll admit, I was pretty skeptical about the XRR thing. Right, because it is such a very, it's a very, very specific technique where you have to be very careful about sample alignment and making sure that the beam is coupled to the sample, and that you have to get like exactly the right
divergence.
Tilt. Maybe your substrate isn't exactly perfectly flat. Like, how do I account for that sort of that sort of introduced error? And it was cool. It was cool to watch the data coming in for the first time and seeing that on something this small and this compact, you're able to do sort of these like higher end diffraction experiments like XRR.
That's right. And so it's all about right tool, right job. So a D8 Discover, like you said, large instrument radius. It's great for those materials research. It's great for thin film. You can fit monochrometers in there. But for powder, you know, this guy, powder.
I think we use the right word.
Yeah.
It's accessible.
That's right.
Right.
It's accessible.
You know, I think about it in terms of, so we joked about your SUV,
Yep,
right? Like
yep,
I've got a small SUV, and it's the right size for when I need to go to IKEA and get a
That's
couple
right.
of things, right?
Yep, yep.
I don't necessarily need a truck, but there are people who need a truck.
That's right.
And it's important that you know someone who has a truck, not to be the one who owns it.
Right tool, right job. That's the way to think about it. Not entry level, right tool for right job. All right, and so with that, if you have any additional questions, you can always send them in to live.events@bruker.com. We'll get those to you. Otherwise, go ahead and feel free to explore our website, bruker.com/d6phaser, to learn more, or check out some of the other videos in our YouTube channel. In fact, there's a really nice video from our launch event posted there where you can hear some of the thoughts and insights from our development team and the product managers and some of the application people, see some of those results. There's also application notes, we've got a brochure, so all kinds of great information. And then, if you happen to be going to any of the conferences,
we'll be everywhere this year.
So Denver X-Ray Conference is coming up in Chicago, got IUCR in Australia, JASIS in Japan, BCEIA, that's going to be in Beijing.
We'll be at American Chemical Society in San Fran, and then MRS Fall
in Boston. And then we've also have Analytica in Brazil. So at any of those places, you'll be able to come out, see this thing in person, get your hands on it, and I'd really, really suggest doing that. Or if you're ever interested in seeing how it looks on your samples or how it works for you, you can always send in samples. We can do virtual demos or visit one of our facilities and see it in person. So thank you, Nate, for joining us today.
Thank you guys for showing up.
Yeah, and thank you to everybody out there. Like I said, this is actually the first of 3 of these that we're going to do to cover the D6 phaser. And until next time, just make sure to keep your signal high and your background low.
Bye, guys.